Rocket science. It's that phrase we use for something that's supposed to be impossibly complicated. But what if I told you that the big idea, the core principle behind every single rocket, from the Apollo missions all the way to today's launches, is actually something you see and feel every single day? Yeah? So let's break it down. Let's figure out how these amazing machines actually conquer gravity.
Okay, so first things first, let's tackle what seems like the biggest puzzle of all. When you're in the vacuum of space, there's nothing. No air to push against, no ground, absolutely nothing. So how in the world does a rocket move? I mean, how does it speed up or even just change direction? It feels like it should be impossible, right? Kind of like trying to swim without any water. The answer to this one question, well, that's the key to unlocking all of space travel. But before we can even think about zipping around in space, we have to beat the very first boss, Earth's gravity. And man, it's this relentless force just constantly pulling everything and everyone back down. So getting this massive, super heavy vehicle to not just lift off the ground, but to completely escape that pull, that is the first and honestly probably the biggest challenge of any mission to space. And the numbers here, they are just mind-boggling. To actually break free from Earth's gravitational grip, a rocket has to hit what's called escape velocity. We're talking more than 25,000 miles per hour. Let that sink in. That's about 7 miles every single second. To put that into perspective for you, that's like traveling from New York to LA in about 6 minutes. It's a speed that requires an amount of energy that's, well, it's almost impossible to imagine. So how do we generate that kind of incredible power? And how do we solve our pushing against nothing problem? Well, the answer isn't some crazy futuristic technology. Nope, it's a fundamental law of the universe, something figured out hundreds of years ago. This right here, this is the secret key that unlocks the door to space. And here it is, Sir Isaac Newton's third law of motion. You've probably heard this a million times in school, but how it's used here is it's pure genius. For every action, there is an equal and opposite reaction. See, a rocket doesn't need to push against the air. It doesn't need to push against the ground. It just needs to push against itself.
Okay, let's make this super simple. I want you to imagine you're standing on a skateboard, right? And you throw a really heavy bowling ball forward as hard as you can. That throw, that's the action. So what happens next? Well, the reaction is that the ball actually pushes you and your skateboard backward. A rocket is doing the exact same thing, just on a scale that is unbelievably more powerful. The action is throwing a whole bunch of super hot gas straight down, and the reaction is that gas pushing the rocket straight up.
All right, so if the whole goal is to throw a bunch of mass out the back as fast as humanly possible, how do you actually do that? Well, you need a machine that's designed for one very specific purpose, creating and directing a massive, continuous, and most importantly, controlled explosion. What you need is a rocket engine. So, what's the big takeaway here? At its very core, a rocket engine is just a device for taking a huge amount of mass, in this case, all that hot gas, and shooting it out at incredible speeds in one direction. And that's what creates that all-important push in the other direction. So let's take a quick peek inside the engine itself. It's like this precise but incredibly violent dance. First, you've got your propellants. That's a fuel plus an oxidizer. Because remember, there's no air in space for the fuel to burn with. They get pumped together into a combustion chamber, and boom, they're ignited, creating this contained explosion. Now, this blast of super high-pressure gas has only one place to go, out through that classic bell-shaped nozzle, which funnels it and accelerates it to supersonic speeds. That right there is the action, and it creates the equal and opposite reaction that we call thrust. Okay, so we've figured out propulsion. Awesome. We've got our engine, it's harnessing Newton's third law, but in solving that one problem, we've just created another one, a new problem that is absolutely massive. I'm talking about the sheer, almost unbelievable amount of fuel you need to pull this off. 90%. Just look at that number. Let it sink in for a second. 90%. What in the world could that possibly be referring to? And here's the answer. For a typical rocket sitting there on the launch pad, a staggering 90% of its entire weight is nothing but its own fuel. The rocket itself, the structure, the engines, that's a tiny fraction. And the payload, the actual satellite or the astronauts that we're trying to get into space, that's a measly 4%. I mean, just think about that. Almost the entire vehicle is just a giant flying gas tank. And this creates this vicious cycle that engineers have a great name for. They call it the tyranny of the rocket equation. See, to get to space, you need a whole lot of fuel, but that fuel is really heavy. So now you need more fuel just to lift that first bit of fuel off the ground, which of course adds even more weight, which means you need even more fuel. It's a huge, huge problem.
So how do you beat this tyranny? How do you escape this loop? Well, you obviously can't carry all that weight with you for the whole trip. The solution is as logical as it is brilliant. As soon as a part of the rocket becomes useless dead weight, you just get rid of it. And this brilliant solution is called staging. The best way to think of it is like a relay race against gravity. The giant first stage, that's your sprinter. It uses an immense amount of power to just blast the whole thing off the ground and through the thickest part of the atmosphere. But once its fuel is gone, it's just a giant, heavy, empty tank. It's dead weight. So, you drop it. The baton gets passed to a smaller, much lighter second stage, which then ignites its own engine and pushes the now much lighter vehicle the rest of the way to orbit. It is the ultimate example of working smarter, not harder, by just shedding useless weight as you go. And there you have it. The whole journey is really just a chain of logic. We start with a problem: how to overcome Earth's gravity. We find the key, Newton's simple law of action-reaction. We build the engine to use that key, a controlled explosion to throw mass. That engine creates a new challenge, the absolutely crushing weight of its own fuel. And finally, we find the solution, shedding that weight through staging. You see? Each step is a direct, brilliant answer to the problem that came right before it. So, it turns out rocket science isn't really one giant leap of impossible genius. It's more like a series of brilliant, clever solutions to a series of massive problems. And now that we understand the incredible physics and the amazing engineering that allows us to get off our own planet, it just leaves us with the most exciting question of all. Knowing how the journey works, where should we go next?